Hi, welcome to Chem with Chem. In this session, we're going to be working question 1 of Chemistry Paper 2 from the January 2020 sitting. If this is your first time to the channel, welcome. Please check out the other materials that are here. Leave a like if you find value, share with your friends, and consider subscribing and turning on post notifications so you can be alerted the moment new material is added. You don't want to miss out. So let us get right into it. Now, this is question 1. Question 1 is normally a data analysis question, and it is valued, or it's worth 25 marks. Please do not spend more than 30 minutes on this question. All right. And in subsequent session, we'll look at how we can, manage our time, techniques we can use to ensure that we finish each question on time and we can get full marks. So let's go right into it. Question 1. The rate of reaction of magnesium with a solution of dilute sulfuric acid can be investigated by measuring how long it takes for a specific volume of gas to be produced. All right, I feel like I'm reading an answer. I'm reading some information right there, crucial. Andrew conducted 2 experiments to investigate factors that can affect the rate of reaction between magnesium and sulfuric acid. In experiment 1, magnesium strips were added to 50 cm³ of 2 moles per dm³ sulfuric acid in a 250 cm³ conical flask. Oh, that's a mouthful. The volume of gas produced over a period of 6 minutes was measured, and some of the measurements are shown in figure 1. The data recorded for experiment 1 are summarized in table 1 on page 6. So before we get to table 1 on page 6, because we don't want to be scrolling up and down, we want to keep the page fixed. We're just going to record the readings and we're going to write them in our table. All right, so let us look at the gas syringe. So these are the readings that we're going to be recording. All right, and a few of them are done for us already, so we just need to record the readings for these. Now, whenever we're reading, whenever we're going to take readings, it's very important that we determine the scale or the gradation on the instrument. So for this gas syringe, each of these little stroke that we're seeing, each of these little marks, each of them represents 1 centimeter cube. And we're looking at what volume is produced at the different times: 0.5 minutes, 1 minute, 2 minutes, 3 minutes, at minute number 4. All right, so we're just going to write these down, and then we're going to fill them into our table in a bit, and then we're going to use them to more than likely plot. That is what question 1 is about: some form of data analysis, mirroring what would normally be done in the lab. So the lab and the theory, everything goes hand in hand. All right, so let's just get right into our reading. So at minute 0.5, that's half of a minute, we have the volume produced here would be 1, 2, 3, that looks like 6, that would be 6 cm³. At minute 2, well, we're not at minute 2 as yet. At minute 1, the volume here is 11 cm³. And at minute 2, this is, let's see, 11, 12, 13, 14, 15, 16. This is 16.5 cm³. At minute 3, this is 19 cm³. At minute 4, the last one, we have, this is, 20, sitting exactly in the middle of 20. So this is 20 cm³. So we're going to take these readings and we're going to fill them out. We're going to fill them out in our table. So just before we fill in those values, as we said, we don't want the page we don't want to be scrolling up and down too much. We're just going to take care of part A before we're going to fill in those values that we just wrote down. Define the term rate of reaction. And this answer was given in a subtle way in the question. Let's just look back at that. This question, this answer was given. The rate of reaction of magnesium with a solution of dilute sulfuric acid can be investigated by measuring how long it takes for a specific volume of gas to be produced. Whenever we're talking about how long, we're talking about time. How long it takes a certain amount of a substance to be produced. It could also be how long it takes a certain amount of substance to be used up. So therein lies our answer. So let's go back down to part 1 of A and answer that first question and just feel good about getting 1 mark, an easy 1 mark. So the rate of reaction is the change in concentration of reactant or product per unit time. In other words, how long it takes a certain amount of a product to be formed, or how long it takes a certain amount of a reactant to be used up. Right, and then we'll move on to part B. Part 1 of B, and we're just going to write in the values that we just read off. So they did at 0 minute, 5 minutes, and 6 minutes for us. So we're just going to fill in our values for half a minute, minute 2, minute 3, minute 4. So at half a minute, we had the volume being 6. At a minute, we had it being 11. At 2 minutes, we had it being 16 and a half. At 3 minutes, 19. And at 4 minutes, 20. Right, so we're going to use these values, so write them down. We're going to use them in the next section. Part 2 of B. Use the data in table 1 to plot a graph of the volume of gas produced against time using the axes below. So we have the data, we just read them off. We're going to just plot. But before we plot, we always need to know the scales on each axis. If not, we're not going to be accurate. Accuracy is very important here. So on the x-axis, we see that for every 2 centimeters that we have, it's been used to represent 1 unit, right? So it means that each of those millimeter, those little ones, would be representing 0.1 minute. And so it means that here we would have 0.5, here we would have 1.5, and so on. So we'd have 0.1, 0.2, 0.3, 0.4, then 0.5, and so on. On the y-axis now, we see where 2 centimeters are being used to represent 5 centimeter cube. So it means that each of these little millimeter box, each of them would be representing 0.5 units or 0.5 cm cube. All right, so we go right into plotting, and please note that they have already plotted 3 for us at 0, at minute 5, and at minute 6, and they've used encircled dots. So we're just going to continue along that line. Okay, so at 0.5 minutes, at half a minute, so let's find half a minute on the x-axis. It's here, so we're going to go up at half a minute. We have the volume being produced. The volume being produced is 6. So right here, the first millimeter after 5 is 0.5. So that's 5.5. Another 0.5 to that will make it 5.6. So that will take us here, and we're going to use let's change to, okay, we can keep this blue. All right, then at minute 1, at 1 minute, 11 cm cube. So this is 10.5. This would be 11. So at 1 minute, 11 cm cube. So we plot at 2 minutes, 16 and a half. Minute 2, so we find 2 on the x-axis and we go all the way up. This is 15, 15.5, 16, 16.5. And I'm just marking it here so we can trace it. You would trace it with a pencil and you rub it off in the exam. All right, and then at minute number 3, we have 19, so we find 3, and we go up to 19. We can just look for the 20 line and we come down 2 spaces. That's one way to go about it. So this is 20, so this would be 19.5, and then this would be 19. So 19 is here. Minute 4 is 20. Minute 4 is 20 cm cubes. So here we are. So we now need to plot, and we want to do that free-handedly. We want to just get one smooth curve going that levels off from 20, levels off, or it starts to level off at 20. So we'll come up. Let's see if we can do this in one go. All right, so we'll work with this one. We want the curve to be a little smoother on the last part, but based on the device I'm using, I'm not getting it like that. We don't want it to be flat right here. We want it to be smooth. So in the interest of time, we'll take this one. Okay, so for the other questions, we're going to let this part remain, and I'll just read the other questions and we'll just answer as we go along. So most of the, a good number of the other questions come from using the graph. So from your graph, so part 3, the first one, using the graph. From your graph, determine the time taken for the reaction to be completed. So if we check the graph, we realize that at minute 3, we had 19 cm cube being produced, and at minute 4, we had 20. And then after minute 4, we still had the same volume. No increase in volume was there. So we had 20 at minute 4, at minute 5, the same 20, at minute 6, the same 20. So it means that this reaction would have come to an end, or this reaction ended from minute number 4. So let's put that down. So it would be minute 4, or we could say 4 minutes. The time taken, 4 minutes. And that would give us the mark. Now, they're also asking in the next question, they're asking part 4. During which time interval was the rate of the reaction fastest? During which time interval was the rate of reaction fastest? And we can look back at for this, we can look back at the table that we filled out just now. So just gonna do a little. So we had the time, and we had in minutes, and we had the volume in cm cube. So if we can get this one without even looking at, without using the graph. We can just look at the table. We can just look to see which time interval gave us the largest volume. We want to say largest amount produced in the shortest amount of time, and that is what would that's how we would know that we had the fastest rate, or during which time interval was the rate of the reaction the fastest. So it would be, looking at the table here, it would be from 0, the time interval would be from 0 to half of a minute, 0 to 0.5. That's the time interval that would have given the fastest rate. Let's just highlight that. So the fastest rate would have been from 0 to 0.5. And this is right here, 0 to 0.5. Let's highlight that on the graph itself. We have the graph being steepest right there. Okay, and if we don't want to answer the other question prematurely. So it's from 0 to 0.5 minutes between. So that's the time interval, 0 to 0.5 minutes. And in part 5 now, they want us to tell or to give the reason, to explain the answer. And so we could state that that part of the curve is steepest, but we can do better than that. We can actually give empirical evidence, all right? Because we can do the actual rate. We said earlier that the rate of a reaction is the changing amount of substance formed or used up per unit time. Per unit time means we're going to be dividing by time, how long it takes. So if we look moving from 0 to 5 seconds, we had no gas at 0, but we had 6 cm cube form, 6 centimeters cube form after half of a minute. So the rate right there would be, so for 0 to 0.5 minutes, the rate would be 6 cm cube over 0.5 minutes, and that would give us a rate of 12 cm cube. That would give us a rate of 12 cm cube per minute, and that was the highest rate for the entire reaction. In moving from half of a minute to 1 minute, the change would have been, let's see, 11 minus 6, that's 5, a change of 5. So that would be 5 over half of a minute, which would be a rate of 10 cm cube per minute. And then if you look at 1 minute to 2 minutes, the change in volume is 5.5 divided by 1 minute. So that would be 5.5 cm cube per minute. And it kept on getting slower, or the rate kept getting lower as time progressed. So the fastest part of a reaction is normally the first part. So we call that the initial rate. So in this case, it would be from 0 to 0.5. And given the reason, we would state that the highest rate of the reaction was obtained there, and we would of course give this part that we have right here. We would give that as our evidence to support that, and we would get our full marks. All right. So part 6 now, they want us to, from your graph, determine the volume of gas produced at 2.5 minutes. 2.5 minutes. So we need to look for 2.5 on the graph. On the x-axis, we're looking for 2.5. 2.5 is here. So we need to draw a straight line using our ruler. Find the volume produced. Wherever that cuts the graph, we would use our ruler again to draw a straight line going across. And wherever that line cuts the y-axis, we read off our values. So we said that we're going up, each millimeter on the y-axis is used to represent 0.5 cm cube. So let's check what we have here. This would be 15.5, 16, 16.5, 17, 17.5, 18. That looks like 18. That looks like 18.5 cm cube. So for part 6, we're going to use the 18.5 cm cube, and let's just highlight that in green. Then we're going to move down to that section. So in part 7, we're going to use the volume that we just found and answer the question. So use your answer in B6 to determine the number of moles of gas produced at 2.5 minutes. So at 2.5 minutes, we just saw that we got 18.5 centimeters cubed. And we're always given something to use. We never left on our own. So 1 mole of gas occupies 22.4 dm cube at standard temperature and pressure. All right, but our value here is in centimeters cubed. So to get a mark, we're going to have to do some form of conversion. So 1 dm cube is the same as 1000 cm cube. So for the first mark, we're going to convert our 18.5 centimeters cube. We're going to convert that to dm cube. So we'll say 18.5 cm cube divided by 1000 cm cube, and that will give us our volume, the volume that we just found, that will give us our volume in dm cube. So we want to keep apples with apples, right? So that's 18.5 divided by 1000. We're going to take that 3 decimal places to the left, which will give us 0.0185 dm cube. Then we're going to start out with a statement of fact. So our statement, so let's keep this by itself. So we'll get a mark for this. Then we'll have our statement of fact, which states from what we're given, 1 mole of the gas we're concerned with, any gas as a matter of fact, occupies 22.4 dm cube. Now we want to find out how many moles, so we put X. How many moles of gas would we have been occupied by 0.0185 cubic decimeters? So we'll cross multiply, and when we cross multiply, we take things across, well, the diagonals. That's a little redundant, but yes, going across. So that X there is not saying it's wrong, we're just going across. So it means then that 22.4 dm cube times X is equal to 1 mole times 0.0185 dm cube. And if we want to make X the subject, we have to get rid of everything that's around X. So we'll need to divide by 22.4 dm cube on both sides. All right, let's use red to cancel out. So 22.4 dm cube, 22.4 dm cube, and whatever we're left with, that will be our answer. So that will be 0.0185 divided by 22.4 dm cube. And of course, we would expect to get less than a mole. So our answer here is 0.0000826. 0.0000826 moles, or we could write that in standard form, 8.26 times 10 to the minus 4 moles. And that would have given us our full marks. So 2 from here and 2 from the conversion that we did earlier. So that would take care of this section. Part 8. Andrew wanted to identify the gas produced. He placed a lighted splint in a sample of the gas, which extinguished with a squeaky pop. Deduce the identity of the gas. So once we hear about a flame, a lighted splint being extinguished with a squeaky pop, then the gas in question is hydrogen. Hydrogen is actually flammable, so that squeaky pop is a mini explosion that we're actually hearing, right? And of course, if it were a larger volume, then we'll probably hear an explosion that is not so squeaky, right? So that would be hydrogen. And of course, be sure to check out qualitative analysis video made simple. Check out the card above for it. There we look at how to identify cations, anions, and also gases, including hydrogen. Part C, and we're almost close to the finish line. We can see the finish line, at least the finish line for number 1. We're almost seeing the 25 marks. We just have 4 left. So we would have already amassed 21. Good, but we want to get better. All right, part 1 of C. Andrew's second experiment required the use of the same mass of magnesium, but in the powdered form, instead of strips. State the factor that Andrew is now investigating. So strip the first time, magnesium strips the first time, but magnesium powder the second time around, but the same mass. Andrew is now looking at the factor of particle size, or what we call surface area. And we would have worked a question similar to this. You can check that out as well. The card is provided above. Similar question. It was just modified somewhat. And part 2, write a balanced chemical equation with state symbols for the reaction that occurred between magnesium and sulfuric acid in the experiment. Magnesium, Mg, it's a solid, plus sulfuric acid, H2SO4, which is aqueous. Acid is in the presence of water, would have dissociated. And of course, it's a metal, reactive metal, and an acid. So we're going to get a salt and a salt, not a salt. We're going to get a salt and hydrogen gas. So the salt here would be magnesium sulfate, which is soluble. So we'd have aqueous. This is AQ, we've written in the little bracket there. What's that, subscript, and then we would have hydrogen. And whenever we write elemental hydrogen, we have to write it as H2. Again, anything that ends in, any element that ends in or gen is diatomic. And let's see, this is it. This is just balance right off the bat for 2 more marks. So for the last mark, to just top this up for 25 out of 25, state one factor other than the factor investigated by Andrew, which can affect the rate of a reaction. And please notice they did not give us any clue here. So we can't use surface area from C1 above. We'd have to state any of the other factors that could actually affect the rate of the reaction in this case. And we're looking at the reaction that Andrew is actually looking at, magnesium and sulfuric acid. So surface area or particle size is out. So the next thing would be temperature. Temperature is another factor that could actually affect the rate of this reaction. Or we could also give concentration. Altering the concentration of the acid would actually could affect the rate of the reaction. All right, and just like that, we would have gotten full marks, 25 marks. All right, and again, we don't want to spend more than 30 minutes max on this question. So thank you for joining Chem with Chem. Be sure to check out the other videos that are on the channel. Please share with your friends, like if you find value, and if you have not subscribed, please consider subscribing and also turning on post notification so you will not miss whenever content like this is added. As usual, copper later.